Hi, my name is Arish Virani, and this is my third lab for Physics 2211, Black Hole and Orbits. So for an introduction, the purpose of this lab is to infer the mass of a central black hole from an orbiting star's trajectory and to design a non-crashing figure 8 style orbit for a spacecraft in a planet-moon system using computation. In part 1, we convert position time data delta t is equal to 1 day into momentum change, applying Newton's second law momentum principle with universal gravitation to compute Fnet and its parallel perpendicular components and estimate the black hole mass from many samples reporting a single value with spread. In part 2, we build a coupled gravitational model, planet-moon ship, choose an initial spacecraft velocity subject to v is less than speed of light, and simulate trajectories to achieve a figure 8 path influenced by both bodies, discussing dominant interactions and modeling assumptions. So for a preview, the star's path is well described by Newton's second law with inverse square gravity, computing Fnet is equal to delta p upon delta t from daily positions and averaging the resulting mass of black hole values. In the three-body planet-moon ship model, adding an outward delta v to the moon's orbital velocity produces a continuous non-crashing figure 8 path influenced by both bodies, illustrating how competing gravitational pulls shape the spacecraft's speed and curvature compared to single-body orbits. So the physics principles and formulas, Newton's second law, we model each body as a point mass and apply Newton's second law in momentum form. From the star's daily position data, we compute Fnet via the first formula on the right, then step momentum, velocity, and position forward. We also split Fnet into components parallel or perpendicular to p. The parallel part changes speed, the perpendicular part bends the trajectory. So for the gravity, gravitational forces are pairwise and add by superposition. For the star, assuming only the black hole acts, the inverse square law plus the magnitude of gravitational force, magnitude of first formula on the right, lets us infer the mass of the black hole at each time step and report a mean plus or minus spread. In the planet-moon ship model, we have some forces from planet and moon on each body every step, keeping v less than speed of light to generate a continuous non-crashing figure 8 influence trajectory. Here are the models and procedure. I'll walk through these in the next few slides. So for part 1, our initial conditions are as such: the gravitational constant is 6.7 times 10 to the power minus 11, the mass of the star is 2 times 10 to the power 30 kilograms, and delta t is a day, 86,400 seconds, and the time for the first observation data point, we're starting at t is equal to 0 seconds. So the system is the star in this case, and the surroundings are the black hole at the origin. So from the star's xy data, I compute velocities between points, then apply the momentum principle, Fnet is equal to delta p upon delta t. That gives a force vector at each time step directly from the motion. I also split it into components along and perpendicular to the momentum, parallel changes speed, perpendicular curves the path. I compare the measured delta p upon delta t with the central inverse square gravitational force pointing to the origin using magnitude of F is equal to gmm upon r squared. I invert for a massive black hole each step, then report a single value as the mean with a spread. Consistent inward direction and stable magnitudes indicate the gravity-only model fits the data. Here are the final results for part 1, and the mass of black hole comes out to be 1.79 plus or minus 0.01 times 10 to the power 34 kilograms. So for part 2, for the planet-moon ship system, our initial conditions are g is equal to 6.7 times 10 to the power minus 11 as before. The mass of the planet is 8 times 10 to the power 27 kilograms. The mass of the moon is 6 times 10 to the power 25. The mass of the spaceship is 7 times 10 to the power 12, and delta t in seconds is 60. And the initial time we're starting as t is equal to 0. When updating the moon, the system is the moon, the surroundings the planet and spaceship. And when updating the spaceship, the system is the spaceship, and the surroundings are the planet and the moon. So for the planet-moon ship system, I use the same momentum principle with superposition. When updating the moon, forces from the planet and ship act as surroundings. When updating the ship, as we mentioned, forces from the planet and moon are surroundings. The aim is a continuous non-crashing figure 8 influence trajectory, so the ship is clearly affected by both bodies. In each step, I form the vector gravitational forces with the 1 upon r cubed direction term, so they point along the separation line, sum to get Fnet on the moon and on the ship, then update velocity and position. The perpendicular component of Fnet steers the path around each body, while the parallel component sets the speed. Here are the final results for part 2, and you can see the ship speed x and the ship speed y. So for assumptions, in general, we are assuming they are point mass bodies. Motion is confined to a 2D plane, constant g, and numerical updates with fixed delta t. For part 1, only the black hole acts on the star, and the black hole is fixed at the origin. The star mass is known, and data spacing through delta t is equal to 1 day. Velocities in delta p upon delta t are from finite differences of xy. Also, any other forces are negligible on the time scale. Part 2, only gravity from planet and moon are included. The planet is fixed at origin, and moon starts circular. V is equal to square root of gm upon r. Ship starts on the moon's surface with v moon plus delta v. We enforce velocities less than speed of light and ignore black hole or star forces here. Assumed distant or weak. We crash if the distance is less than the radius. So overall analysis and discussion. Data versus model part 1. The inferred Fnet is equal to delta p upon delta t points nearly radially inward, aligned with negative r hat, consistent with an inverse square central force. Black hole mass estimates mass of black hole is equal to the magnitude of force times r squared upon gm star. A cluster around a single mean. Spread arises from daily sampling, small curvature or speed changes, and step size error. Reporting mean plus or minus standard captures the central value and variability. Trajectory behavior for part 2. With a slight outward delta v, the ship's path is influenced by both bodies, continuous, non-crashing figure 8-like loop. Sensitivity delta v and delta t matches 3 body expectations. Too little delta v would lead to lunar re-impact. Too much delta v would lead to planetary escape. So sources of discrepancy are error, finite difference velocities, forward difference noise, fixed step size, treating massive bodies as fixed, ignoring additional forces, black hole or star in part 2, and collision handling thresholds. Using central differences or smaller delta t would tighten the mass of the black hole spread and reduce trajectory drift. So what does it mean, part 1? How the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. Rate of change of momentum, delta p upon delta t, is measured from position data, what the star actually did. Net force, Fnet, is the cause, defined by the physical model, sum of interactions. By Newton's second law, they are equal, but their interpretations differ. Parallel components change speed, energy. Perpendicular components bend the direction curvature with little immediate speed change. Agreement of measured delta p upon delta t with modeled central F validates the gravity-only assumption. So what if this imaginary system in part 2 has a black hole, a star, a planet, and a moon? If you wanted to predict the motion of the entire system, what would you need to include in your computational model? To predict black hole, star, planet, moon ship together, include all pairwise gravity, superposition, realistic initial conditions, and a long-term stable integrator. Dominant interactions typically rank black hole and star greater than the star and planet, greater than or approximately equal to the planet and the moon, which is greater than the planet or moon and the ship. Distance of black hole or star pulls on moon or ship may be small but can accumulate over long times. We can expect precision and sensitivity to initial conditions and monitor energy or angular momentum drift to assess numerical error. So in conclusion, the star's motion fits a central inverse square gravity model. Delta P upon delta T points inward, and the stepwise estimates converge to one black hole mass, mean plus or minus spread. In the planet moon ship model, a small moon frame delta V yields a stable non-crashing figure 8 influenced by both bodies. Minor mismatches come from difference in noise and fixed time steps, but overall the results support Newton's second law and universal gravitation. Thank you.